Okay, let's get a surface area on this guy. This curve up here, y equals square root r squared minus x squared, you should recognize as the equation of a semicircle. So I know this is part of a circle because if I square both sides, I get y squared equals r squared minus x squared, which is the same as x squared plus y squared equals r squared, which is a circle of radius r centered at the origin. So I'm told to take only the chunk of this on 0 to r, which is what I kind of outlined in red there, and then I revolve it around the y-axis. And so this traces out a hemisphere, and I'm trying to get the surface area of it. So you may recall that for an entire sphere, the area is 4 pi r squared. And so what we're expecting to get here is 2 pi r squared. So I'm going to mark off a little area of arc. I like to call that ds, and that's given by the arc length formula. And then we're going to let that follow the revolution around the y-axis. All right, probably not a lot to be gained by trying to do better than that. And this is a little ribbon of surface area. So I need to get a radius on this ribbon because I want the area of it. And I'm just at some arbitrary horizontal location x here, so I can just say that radius is just x. And then the thickness of that little ribbon is going to be given by this formula. So it looks like we have to compute f prime or y prime. I think we should probably just do that before we start doing anything else. So this is r squared minus x squared raised to the 1/2. So I end up with 1/2 r squared minus x squared to the negative 1/2. And then the chain rule says you've got to also multiply by a negative 2x. That's the derivative of the interior. So the 2's cancel, and I end up with a negative x. And then this thing to the negative 1/2, that means 1 over the square root. So that's going to be square root r squared minus x squared. And then I'll go ahead and square that as I'm setting up the integral. So let's slice and unroll this little ribbon. And the thickness there is ds, and the circumference is 2 pi times the radius, so 2 pi x. So my little differential contribution to the area is 2 pi x ds, which can also be written as 2 pi x square root 1 plus the derivative of y squared. So when I square this thing, I end up with an x squared over r squared minus x squared inside that square root. And there's my dx. So I'll go ahead and just write this total area as an integral now, and then we'll get into the algebra of how you grind through the integral. So the total area is going to be the sum of all the contributions to area. So I'm adding up dAs. I've written dA entirely in terms of x, so now I can say I'm adding these up as I go from x equals 0 to r. Every one of these x values corresponds to a ribbon that's going to build the entire hemisphere. And I'm going to do some cleaning up of the square root as I go. I can call 1 r squared minus x squared divided by itself. And then then in this second term I have an x squared over that. Now that I have a common denominator, I can just add those numerators together. I suppose it'll work over here. Okay, so I have r squared minus x squared plus x squared. All right, the x squareds cancel out, and I have an r squared in the numerator, which if I take it out of the square root becomes an r, so I may as well do that. All right, then I can show this 1 over square root as just this thing, r squared minus x squared to the negative 1/2. And what I notice is a function of an expression here, r squared minus x squared, sitting right next to the derivative of that expression almost. The derivative of this interior expression is negative 2x, and I have the right function piece over here to get that done. So I'm going to modify this integral to put a negative 2x in here, moving all my other constants outside. So the 2 is going to hang out with the x, that's staying in there, and then I'm multiplying the interior by negative 1 and the exterior by negative 1. A pi and an r can be taken out. And you should double check when you're messing around like this, that when you distribute those constants back into the interior, you get what you started with. So there would be a 2 pi, it would be positive, there's an x and there's an r, so that all looks good to me. All right, so the whole point of that was to recognize the effects of the chain rule. So I have this thing to the negative 1/2 sitting next to the derivative of that thing. So that must have come from differentiating r squared minus x squared to the positive 1/2 divided by 1/2, which is the same as multiplying by 2. Now if you don't believe me, just give it a try real quick. You bring down the 1/2 and it cancels the 2. So if I differentiate this, I subtract 1 from the exponent and I end up with the negative 1/2. And then the chain rule says multiply by negative 2x. So I would get back to the integrand I started with. That's just an informal way of looking at substitution. Now I evaluate from 0 to r. And when I plug in the upper limit here, I get r squared minus r squared, which is 0, so I'm just going to cross it out right there. Then I subtract what I get when I plug in the lower limit, and that's going to kill the minus sign. So I have out in front, let me just clean that up real quick. Out in front, I have a 2, a pi, and an r, and I'd rather write that as 2 pi r. And then when I plug a 0 into this term, I end up with r squared to the 1/2. Which is just r. And so I end up with 2 pi r squared, which is half the surface area of a sphere, exactly what I expected to get out of this problem.